All right, so in the previous section, 7.2, we talked about how to define the 6 trigonometric functions: sine, cosine, tangent, secant, cosecant, and cotangent. And we used the right triangle idea to define all of those. Now, that was fine for that section, but it turns out that using a right triangle to define those trigonometric functions actually puts way too heavy of a restriction on those functions to make them useful. And the reason for that is because if we're defining the sine or cosine or tangent or any of those trigonometric functions in terms of that right triangle, we're always plugging an acute angle into one of those trigonometric functions, some angle between 0 and 90 degrees. That means that using a right triangle, we don't have any way of determining the sine of 200 degrees because that's not an acute angle. But we do have a meaning for a 200-degree angle, so it would be nice to be able to take the sine or the cosine of it. Same thing with negative angles. You know, we don't have a way of taking the tangent, for example, of negative 60 degrees. Because a negative 60-degree angle is not an angle that's possible in a right triangle. So how do we deal with those types of angles in our trigonometric functions? In fact, we can't even take the sine or cosine of a 90-degree angle because the two acute angles in a right triangle cannot be 90 degrees. How do you deal with that? Well, in order to do that, we have to expand our definition of the sine and cosine functions. We need to expand our definition of the other 4 functions as well, but we deal with those functions in section 7.4. Right now, our focus is just the sine and the cosine functions. So, what we're going to do is take the right triangle idea and embed it inside what we call the unit circle. So if you don't remember what the unit circle is, it's a circle in the coordinate plane centered at the origin with a radius of 1. Unit means 1, so that's why we call it the unit circle. Okay. Now let's suppose because we're in the coordinate plane, I can put angles in standard position here. Let's suppose I have some angle T. It's in standard position, and it happens to be in the first quadrant in this example. Notice that angle T, its terminal side, you can cut its terminal side to the radius of this unit circle, or to make it a radius of this unit circle. So basically, it goes from the origin, and then I make it stop here at the unit circle instead of extending forever in that direction. In that sense, the angle T determines a specific point on that unit circle, the point that intersects the terminal side of that angle. I'm going to call that point XY. Okay? Now, what else do we know from this image? Well, first of all, because this terminal side here is a radius of that unit circle, and the radius of the unit circle is 1, then that side has a length of 1. Okay? What else do we know? Well, if I were to drop a perpendicular from this point XY down to the x-axis, then I can create a right triangle inside this unit circle where the radius of this unit circle is used as its hypotenuse. So you can see this right triangle right here. Now that we've embedded a right triangle inside our unit circle, we can come up with the sine and the cosine of that angle. So remember, but let's back it up a second. Before we do that, the coordinates of this point x and y are actually going to determine the base and the height of this right triangle because of where it's positioned in the plane. So for example, the height of this right triangle would be the same thing as the y coordinate of this point. So the height is y. The base of this right triangle would correspond to the x coordinate of that point. The x coordinate would be the same as the length of our base. So that would be x. So what does that mean if we were to look at the sine and cosine of that angle T? Well, what is the sine of T? Sine of T should be opposite over hypotenuse. That would be y over 1. Similarly, the cosine of T should be adjacent over hypotenuse, which in this right triangle is x over 1. Both of those simplify. Sine of T is y over 1, which is the same as just y. Cosine of T is x over 1, which is the same as x. What that means is that the x and y coordinates of that point on the unit circle are exactly the same thing as the cosine and sine of t respectively. So that the coordinates of this point here correspond to the cosine and the sine of this angle. Okay? I indicate that here. If xy is a point on the unit circle determined by some angle t, then the x-coordinate is the same thing as the cosine of t. The y-coordinate is the same thing as the sine of t, based on that little derivation that we just looked at. Okay, now what does that actually do for our goal here? Remember, the goal of this unit circle is to be able to extend the domain of our sine and cosine functions. That means it should be able to give us the ability to plug in more numbers than just 0 degrees to 90 degrees or 0 degrees to pi over 2, or sorry, 0 radians to pi over 2 radians. And here's how we're going to do that. The point xy does not have to live in the first quadrant. It can be anywhere else on the unit circle. In fact, if t is any angle at all, even if that angle is more than 360 degrees, even if that angle is negative, that angle will determine some terminal side that can be thought of as a radius in this unit circle, which will determine some point on this unit circle. The x and y coordinates of that point, then, are how we define the cosine and sine of that angle. Okay? So we define cosine of t, now no matter what t is, to be the x-coordinate of that point. Sine of t is defined to be the y-coordinate of that point. So we're going to do some examples to illustrate this. And in order to do that, we're going to have to make use of those reference angles we talked about back in 7.1. So let's come up here. Notice we're doing sines and cosines of a few different angles here. And all of these angles are not acute. So we can't use the right triangle idea. If I wanted to find the sine of 135 degrees, you cannot fit a 135 degree angle into a right triangle. It just won't work. But the unit circle allows us a method for doing this. Okay, so I'm going to sketch my unit circle in here. All right, where is 135 degrees? Well, that would be in the second quadrant right here, okay? This is a 135 degree angle right here. 135 degrees. How do I find my the sine of 135 degrees? Well, the sine would correspond to the y-coordinate of this point right here. But now I have to figure out what the y-coordinate of that point is. Well, as we saw before, if I take this point and drop a perpendicular to the x-axis, it creates this right triangle for me. And I already know that the hypotenuse of this right triangle is 1, and that's not really going to matter so much because what we need is the y-coordinate, which would correspond to this side right here. Y, that's x right there. How do I get that? Well, if I can figure out this angle right here, which would be the reference angle for the 135 degree angle right there, then I could use that in my right triangle. Notice the reference angle is contained inside this right triangle, whereas the 135 degree angle is not. From how we calculated reference angles back in section 7.1, I see that these two angles go together to make a 180 degree angle, which would mean that my reference angle is 180 minus 135, which equals 45 degrees. That makes this a 45 degree angle, okay? Now, how do I find y? Well, sine of 45 degrees, as we saw back in 7.2, is root 2 over 2. It's also, sine of 45 degrees would be y over 1, the way that I've labeled this right triangle. Y over 1 is the same thing as y. So the y-coordinate is the same thing as sine of 45 degrees here. That would make the y-coordinate root 2 over 2. Now I don't actually need the x-coordinate because the x-coordinate tells me the cosine of that angle, but let's go ahead and find that x-coordinate anyways. Notice that this right triangle would be a 45, 45, 90 triangle, which means the legs of this right triangle are equal. The x value here would also be root 2 over 2. But wait a minute, we need to be careful, because even though the base of this right triangle is root 2 over 2, look at what quadrant we're in. The x-coordinate of all the points in the second quadrant should be negative. Negative root 2 over 2. Okay? Now, again, because we're looking for sine, I want the y-coordinate, not the x-coordinate. This means the sine of 135 degrees is root 2 over 2. And again, it corresponds to the y-coordinate of that point. Let's try this with a different example. I want to find the cosine of negative 60 degrees. The very first thing I need to do is determine exactly where negative 60 degrees is within the unit circle. So I sketch out this unit circle. Negative 60 degrees, the negative means we rotate clockwise instead of counterclockwise. It's going to be down here. Okay, so that's my negative 60 degree angle. And as before, I drop a perpendicular to the x-axis, creating what this time looks like an upside down right triangle. That vertex of the right triangle corresponds to a point on the unit circle that has an x and a y coordinate, and the x-coordinate of this point is equal to the cosine of this angle, negative 60 degrees. So what is the x-coordinate of this point? Well, what's the reference angle that we're using here? The reference angle is 60 degrees. Okay? So if we have a 60 degree angle in this right triangle, we're talking about a 30, 60, 90 triangle. And if my hypotenuse is 1, then the x-coordinate of this point, which corresponds to the base of this right triangle, would be 1/2. And again, it's because that shortest side of a 30, 60, 90 triangle is half the hypotenuse. The other side here would correspond to root 3 over 2, except, wait a minute. Just like in the previous example, I need to make sure that I'm using the correct signs for the coordinates of my point here. So my x-coordinate, because we're in the fourth quadrant, all of the x-coordinates of the points in the fourth quadrant are positive. We already know this. But the y-coordinates are negative because they are below, all these points are below the x-axis. Okay, cosine of negative 60 degrees, I would be using the x-coordinate. By definition, the cosine of negative 60 degrees should be the x-coordinate of this point. So that's equal to positive 1/2. Okay? Let's look at another one. This time let's work in radians. So sine of 7 pi over 6. How do we evaluate this? We're going to begin with our unit circle. Okay, and radians, it's a little less familiar territory for most of you, but you know, we've done some practice with this. Remember, a 180 degree angle is the same thing as pi. 7 pi over 6 would be a little bit greater than pi. So this is the angle that we're talking about. That's 7 pi over 6. Notice it determines a point here in the third quadrant, so I would say that this angle is in the third quadrant. And dropping a perpendicular there creates a right triangle. Okay? Because we're evaluating sine, what we want is the y-coordinate of this point. By definition, that's what the sine of 7 pi over 6 will be equal to. Okay? Well, what is my reference angle here? My reference angle is 7 pi over 6 minus pi. Notice that would leave me with just this angle right here. That's equal to pi over 6. Okay? So we're looking at a reference angle of pi over 6. That reference angle is the key to finding the cosine and the sine of this angle 7 pi over 6. From our previous work, in that table we created in the previous section, we saw that the cosine of pi over 6 was root 3 over 2, and the sine of pi over 6 was 1/2. Okay, so next thing we need to do is determine whether these should be positive or negative or some mix of the two. Well, what do we know about the coordinates of the points in the third quadrant? Because they're to the left of the y-axis and below the x-axis, both the x and y coordinates of any point in the third quadrant should be negative. So back to what we were looking for. Sine of 7 pi over 6 should be the y coordinate of this point, which turns out to be negative 1/2. Okay? Finally, we need cosine of 5 pi. So, okay. Now 5 pi is more than one full revolution around that unit circle. Remember, 2 pi is a full revolution, and 5 pi is equal to 2 pi plus 2 pi plus pi. Each of these 2 pi's corresponds to one full revolution around the unit circle. So if I go 2 pi, and then another 2 pi, and then a pi, that lands me right here. Now notice I can't drop a perpendicular to the x-axis from this point because that point is on the x-axis. But the nice thing about that is we know the radius of this unit circle is 1. So what does that tell me about the coordinates of this point? Well, this point is on the x-axis, which means its y-coordinate is 0. And its x-coordinate is 1 unit to the left of the y-axis. That means its x-coordinate is -1. So that tells me that the cosine of 5 pi, which should be equal to the x-coordinate of the point determined by that angle right here, that would be -1. Okay? For examples, we could do lots and lots and lots more, and you will in the homework. It's important practice. But we'll return to this idea in a moment. Next thing I want to talk about. This might be the most important identity that we cover in trigonometry. It's certainly the one that we end up using the most, especially in chapter 9. We call this the Pythagorean Identity. There's actually 3 identities that we refer to as the Pythagorean Identity. This is kind of like the main one, but we're going to define or derive the other 2 from this in 7.4. So where do we get this Pythagorean identity from? Well, remember, the unit circle is something that we learn about in algebra. I just pointed to the unit circle when it was off the screen. Here's a unit circle right here. We learn about circles in algebra, specifically intermediate algebra, when we talk about conic sections. And the unit circle is centered at 0, 0, the origin, and has a radius of 1. From what you know in algebra, the equation of the unit circle would look like this: x squared plus y squared equals 1. So if xy is any point on the unit circle, then x and y are related by this equation. X squared plus y squared equals 1. Okay? Now, not only that, but we just made a connection in this section between a point on the unit circle and the angle that determines that point. So if t is an angle that determines the point xy in the unit circle, from our definition, we know that x is equal to cosine of t, y is equal to sine of t. But if that's the case, I can use cosine of t and sine of t as substitutions for the x and the y respectively in this equation, and that gives me cosine squared of t plus sine squared of t equals 1. Now, we haven't used this notation yet, so I want to mention something about this notation. When I say cosine squared of t, what I really mean is this: cosine of t squared. And when I write sine squared of t, what I really mean is this: sine of t squared. That notation means that we do the cosine or the sine first, and then we square the result of that. Squaring is the last thing that we do. The notation seems to indicate that that's in reverse order when it's not. Okay? Let me give you an example of using the Pythagorean identity. Let's suppose for a moment that theta is an angle in the third quadrant, and we want to suppose here that we know the cosine of theta. Cosine of theta happens to be -4/5. Can we use this to find sine of theta? Well, yes, the Pythagorean identity is our key to doing that. According to the Pythagorean identity, cosine squared of theta plus sine squared of theta is equal to 1. Okay? But cosine is equal to negative 4/5. So if I plug that in here, negative 4/5 squared plus sine squared of theta equals 1. What is negative 4/5 squared? It's 16/25 plus sine squared of theta. Now, I'm going to be doing some arithmetic with fractions here, so it would be helpful if I had a common denominator. Let's turn the 1 into 25 over 25 so that these two fractions have common denominators. Subtracting the 16/25 from both sides, I get sine squared of theta equals 9/25. Now, how do I solve for sine of theta? Well, remember, sine squared of theta is the same thing as this. If I want to get rid of the second power, I can take a square root of both sides. Sine of theta is the square root, it's equal to plus or minus the square root of 9/25, which is 3/5. Now remember that anytime you take the square root of both sides of an equation, you have to pick up this plus or minus here. That's a necessity. But the sine of theta can't equal two different numbers. It's a function. It should only have one output for any given input. So we have to determine whether this is a positive 3/5 or a negative 3/5. And that's the reason why we name which quadrant we're in. Remember, from this example up here, when we had an angle that was in the third quadrant, the point that determined had a negative x and a negative y coordinate. That's true of all points in the third quadrant. So if sine of theta corresponds to the y coordinate of that point, then that y coordinate would have to be negative. So we don't want the positive, we want the negative 3/5. Negative 3/5 is the answer there. Okay? All right. One last thing. This section is a little bit shorter than the previous two. Back in 7.2, we created this table. Right, and in that table, we we found the sines and cosines of three specific angles: 30 degrees, 45 degrees, and 60 degrees. We can plant those here in our unit circle. So in the first quadrant, if you focus on this, this is our unit circle. I have all three of those angles labeled: 30 degrees, 45 degrees, 60 degrees, as well as their radian measure: pi over 6, pi over 4, pi over 3. Now, let's look at the cosines first. From the table in that previous section, we saw that cosine of 30 degrees was root 3 over 2. That's why this x-coordinate is root 3 over 2, because that's where our cosine should be. Cosine of 45 degrees was root 2 over 2. Cosine of 60 degrees was 1/2. So that gives us the x-coordinates of all three of those points. And here's the sines. Remember, we noticed that the sines and the cosines of these three angles seem to be the same, but in reverse order. So 1/2 root 2 over 2, root 3 over 2. There's a couple of other angles worth noticing that are near these three. The quadrantal angles 0 degrees or 0 radians, and 90 degrees pi over 2 radians. As we saw in this example over here, when we have an angle that's quadrantal, so 0, pi over 2, pi, 3 pi over 2, 2 pi, any of those, we can't create a right triangle, but it's easy enough to determine what point that is on the unit circle, because it's always going to be on an axis, making one of our coordinates 0 and 1 unit away from the other axis, which will give us a positive or negative 1 for the other coordinate. So for example, right here, this is the point 1, 0. That means that the cosine of 0 degrees is 1 and the sine of 0 degrees is 0. Similarly up here, 1 unit above the x-axis on the y-axis, that's where this point would be, it's going to have coordinates 0, 1. So the cosine of 90 degrees, which is what determines this point, has to be 0, and the sine of 90 degrees would be 1, the y-coordinate of that point. Okay? So here, 1, 2, 3, 4, 5 different angles, 0, 30, 45, 60, and 90 degrees. We can find the sines and cosines of those angles all by using this unit circle. How then do I get all of these other side, all of these other values in my unit circle? Well, we've already shown how we've gotten some of them. For example, the very first example that I did here, I found the sine of 135 degrees, and we did that by using this reference angle idea. I just found what a 135 degree angle would look like, found that the reference angle happened to be one of those special angles that we like to talk about, 45 degrees, and that allowed me to determine the x and y coordinates of this point. What we're seeing here is what we would get if we did the same thing with all of these points after reflecting them across the axes. So for example, a 45 degree angle, if I reflect it across the y-axis, takes me to this 135 degree angle. That reflection is not going to change the y coordinate of that point because it's a horizontal reflection. That point doesn't move up or down. That's why my y coordinate for both of these points is root 2 over 2. However, the x coordinate of this point does move. It moves from being on the positive x-axis to being on the negative x-axis, but the same distance from our y-axis. That means that my x coordinate changes sign as I go from this point to this point. Okay, and I can see that same relationship if I reflect any of these other points across the y-axis or similarly across the x-axis. We get a similar relationship. And this thing is what we call the unit circle. I know I've been using the term unit circle just to talk about the circle itself, and that's what you would use to refer to that circle in algebra as well. But in trigonometry, when we say use the unit circle for that problem, what we're talking about is using this entire diagram here. Ultimately, this is something that you want to memorize. I know that that seems like way too much to digest, but there's a lot of very useful patterns inherent in here. And I did mention previously that one of those patterns becomes apparent when we rationalize denominators, getting these radicals in the numerator like we have here. So let me investigate this for a moment. I'm going to create a little table down here, just taking us through the first quadrant. Okay, so we're going to look at sine of theta and cosine of theta for the following angles. So we're going to do 0, 30, 45, these are all degrees, 60 degrees, 90 degrees. Okay? We have all those values up here. So using the unit circle, I know it's off the page now, but if I were to go through and look at the signs, I would find that sine of 0 is 0. Sine of 30 degrees is 1/2. Sine of 45 degrees is root 2 over 2. Sine of 60 degrees, root 3 over 2. Sine of 90 degrees is 1. Okay? Now, notice that all three of these fractions have 2's in the denominator. Okay? And the numerators, some of them have radicals. What if I tried to make all 5 of these values look similar? In other words, what if I wanted to have all of them with a 2 in the denominator? I really needed to leave myself more space here. Denominator. Okay? And what if I wanted to have a radical in each of their numerators? Well, 0 is the same thing as 0 over 2, and 0 is its own square root. So I could write that as root 0 over 2. 1 is the same thing as the square root of 1. So 1/2 is literally the same thing as root 1 over 2. Root 2 over 2 is already looking the way I want it to look. Same with root 3 over 2. What about 1? Well, 1 is equal to 2 over 2, and 2 is the square root of 4. Now I know that's a little sloppy, but here's what we just found. These are the special angles. If you can remember these in this order, 0, 30, 45, 60, 90, then we know that the sine, at least, of any one of these angles is going to look like the square root of something over 2. And look at the radicands, the things inside the square roots. It starts at 0 and counts its way up to 4. 0, 1, 2, 3, 4. So what if I wanted to find, for example, the sine of 60 degrees? I know it's right there in my table, but what I would do is I would think, what are my special angles, and count my way up to 60 degrees. That's 0, 30, 45, 60. It's the 4th number in that list. If I count if I count 4 times, but starting at 0, 0, 1, 2, 3, that tells me what to put in the radical, and my denominator should always be a 2. Okay? It's going to take some time for that pattern to sink in if you want to use that pattern to help memorize the unit circle. But that's the way I like to think of it. I'm not going to fill out this part of the chart because it's just going to be the same values but in reverse order, so you can kind of pick up on that pattern there as well. This unit circle is extremely, 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 extremely important in trigonometry, and it is absolutely critical that you ultimately memorize this thing. The pattern I showed below is a good way to help memorize it, but however you choose to do it, you have to know this thing. It's going to be critical for the rest of the course. Okay, so I think I have made that clear. This is it for section 7.3.